Hello everyone. Welcome back to Chapter 9, Radioactivity or Nuclear Radiation. In this section we're going to look at nuclear equations. And we're going to learn how to balance these, and I'll have to tell you, as far as balancing things, I think these are like the easiest ones in the universe. In a balanced nuclear equation, you're going to see that particles have been emitted from the nucleus. Remember, that's the definition of what's happening here. The mass number and the atomic number may change, okay? But the sum of the mass numbers and the atomic number must be the same on each side of that arrow, all right? So, for example, if you have a nuclear material with 251 as its mass and 98 as its atomic number, and they give you this as the reaction that's going to occur, and so we can see here that it's what, an alpha emitter. Okay, so we have 251 over here, and if we know it's an alpha emitter, there's 4 on the top number, and so 4 and some number has got to equal 251. Okay, so what you do is you can subtract 4 from 251 and would know that that was 247. Same thing with the number on the bottom. It's 98 over here. You've got to equal 98 over here. So 96 plus 2 equals 98. All right, see how that works? So when we're writing these nuclear equations and balancing them, the first thing you do is you write the incomplete equation. You determine what mass is missing. You determine what atomic number is missing. Then you've got to figure out from the new atomic number, if it is a new one, what the new symbol is, because if the atomic numbers change, that means the number of protons have changed. So it has to have a new number. A new name. And so we have to determine that symbol, and then you complete that equation. So when the radioactive nucleus emits an alpha particle, a new nucleus forms with a mass that is decreased, because remember your alpha particle is this. So what's formed is it's going to lose this 4 mass and 2 atomic number and form something new that has possibly, yes, actually definitely a different characteristic, because it's going to be a completely new atom. All right, so you've decreased the mass by 4 and you've decreased the atomic number by 2, and so it's not uranium-238 anymore, because that's a 92 atomic number. It goes to something with a 90, and so it's thorium. Okay, so thorium and an alpha particle are what it takes to balance that U-238. So an equation for an alpha emission, in this example, you've got radon 222. That means the mass is 222. The atomic number is 86. We're saying it's going to go through an alpha decay. All right, so that means that it's going to lose 4 on the top and lose 2 on the bottom. Okay, so here you go. This is the really hard part. 222 minus 14 is 218. 86 minus 2 is 84. So this right here is going to become 218 and 84 on the bottom, and so you've got to figure out what that 84 goes with, and if you look at the periodic table, you'll see that 84 is polonium, and so 218 over 84, and the new symbol is polonium, and that is it. Okay, you don't have to do all this back and forth stuff. All you have to do is make sure that your masses and your atomic numbers balance. In a beta emission, remember a beta is a high energy electron basically, and electrons are very, very light. So an electron doesn't have mass, but it has a negative charge typically. All right, and so this beta particle is going to be emitted from a nucleus when it breaks down, and it's going to increase the atomic number by 1. Why is that? Okay, well, if you start out with 42 mass and 19 atomic number, and you're going to get rid of a negative, okay, and remember back when we were doing charges, if you have gotten rid of a negative, okay, what have you done? That electron has to go somewhere, and so if this is giving an electron to something, this number will now go to what? 20. Because this one's 19, this one on this side has to be something minus 1 equals 19. And of course, there is no mass in an electron. So the mass stays the same. The atomic number goes to 20. And if you look on the periodic table, you see calcium is atomic number 20. And so what you've done is you have taken potassium 42 and converted it to calcium 42 and what? A beta particle. So then you see 20 minus 1, positive 20, is the same as 19. And 42 over here, and 42 minus 0 is still 42. So let's try our learning check. Put me on pause for a minute and see if you can do this, and then come back and we'll work it together. Alright, so we're going to do the beta decay of cobalt 60. Okay, so first we're going to do is we're going to write this, the formula as far as we can do it, the equation. So alright, so we know that we're starting with cobalt 60. And so we're going to have to look on the periodic table to figure out what atomic number cobalt is. And it's one of the transition elements, so it's 27. You should be able to look on there and find cobalt, and it's 27. Alright, and we know that it's going to go through beta decay, and so we remember that a beta particle is a high energy electron, or you can look on the chart. And so something here is what we need to find. This is all we need to find. Okay, so we've got 60 over here, and we need 60 over here. Okay, and 60 minus 0 is what? Or plus 0 is still 60. So we'll still have 60 on the top. With me so far? We've got 27 over here, and we've got a negative 1 over here. So what minus 1 equals 27? I know that's high in math, right? 28. Yes, 28 minus 1 is 27. So you have a 28 on the bottom. Then you have to look and see which element is number 28, and you will find, I believe, that it is nickel. And so our balanced equation is cobalt 60, beta decays 2, nickel 60, plus a beta particle. Don't you love these? In positron emissions, a positron, and this one's easy to remember because you've got an alpha particle, which is basically a helium with a 4 and a 2 on it. Okay, then you've got a beta, which is the next one, which is a high energy electron. The positron is just a positively charged electron. Okay, so basically what happens is when you emit in a positron format, you take a proton, which is hydrogen, right? And it becomes a neutron, and it becomes an electron. Okay, so the electron plus the neutron is what's left after you get rid of energy from this proton. So the mass number of the new nucleus is still the same, right? Just like we saw with the beta particle, but the mass of the atomic number is going to do what? Decrease by 1. Why? Because now instead of 25 over here, you're going to be adding 1. Okay, so you have to say 24 plus 1 equals 25. Okay, now you can look in the book and you can look at the learning checks as they've worked them out and everything, and they do it a little bit different. You know, they do minus a negative or whatever. This is just my way of doing it, and either way is fine. So you can just look at that and see which one works best for you. In gamma radiation, notice the gamma symbol we said is 0, 0. So all it is energy. So it's not going to affect the mass or the number. So the only way we can really tell that something's different is by putting this M here. Okay, and so the M is the unstable nucleus, and without the M is the stable form. So it's gotten rid of that excess energy so it can be stable again. Okay, so the mass and the number will stay the same. We just get rid of that M, and then of course you're going to be plus that gamma. And it's high energy, very high energy. All right, so basically to summarize those radiations, we have an alpha. When you emit an alpha, you're going to produce a helium atom plus whatever that new element is. The mass will be 4 less. The atomic number will be 2 less. And if it's a beta emitter, it's going to be getting a negative charge over here. So the new element will have the same mass, but the atomic number will have to be 1 higher. A positron, basically the same as a beta emitter, except this number is positive instead, will also give you a new element, but the atomic number will be less than 1. 1 less, sorry, than it was before. And then finally, the gamma emitter doesn't change anything, but it goes from the M form to the stable form. And that's all there is to that. Now, to produce these radioactive isotopes, what happens basically is that you bombard it with something. If you have something that's stable and you want it to become radioactive, you can do something called transmutation. Sounds kind of like scientific craziness, right? When you take a stable nucleus and you convert it to the radioactive form by bombarding it, or you may have heard the word colliding it with some particle, okay, like super colliders and things like that. That's what they're doing. All right, so if you have boron 10 and you bombard it, so it's not emitting this time, you're actually hitting it. Like, I don't know if you've ever played pool or billiards or whatever, but it's like taking the cue ball and smacking it into that stable boron nucleus. What happens is that part of that helium sticks to the new one and it spits out a neutron. Okay, so you take the helium and the boron and you actually increase the number from 5 to 7, and while you're doing it, you're kicking off a neutron from this new part. Okay, so let's look and see what this is. Now, this is an alpha particle, but what we've done this time is instead of emitting something already radioactive and then decaying by giving off an alpha particle, we're on purpose hitting a stable nucleus with the alpha particle and causing it to become unstable. That's why it's got these crazy little lines trying to show you it's like, you know, we're freaking out a little bit. So you balance the same exact way, okay? It's still super easy, but this time you got the particle on the left-hand side instead of the right-hand side. So on above it, you've got 98.1 is 99, and 27.0 plus 0 is 27. All right, and then you've got 4 and a 2. So you need for this to be 99, and you need for this to be 27. All right, so what plus 4 is 99? Okay, if you want to think about 99 minus 4, that gives you what? 95. And then what plus 2 gives you 27? 25. All right, and so what we have to do is we have to look and see what is 25. And I believe number 25 is manganese, if I'm not messing up completely. And so we should have manganese 95. So our reaction will be whatever that is, I don't even remember, plus a what? Alpha particle? Oh, wait, sorry. We're hitting it with a neutron, and we're releasing the alpha particle. That's why we got this on this side, okay? So, yeah, you're probably sitting there thinking, she has lost her mind. All right, so we added a neutron, okay? So we used the neutron to bombard with, and then we produced an alpha particle and whatever this new manganese is. Basically, you just do these little numbers when you have them. All right, so 98 TC98 plus a neutron is going to give you our manganese that we calculated plus our beta particle, which it gave us. Okay, so we bombarded with a neutron, and so when we hit this with this neutron, then we made manganese, and then we split off that alpha particle and released it. That's the end of 9.2. Okay, so I know I kind of like butchered that a little bit, but just remember that when you get a equation like this, all right, just look at it and see, okay, this was our thing that we were going to have to figure out. So 98 plus 1 and 27 plus 0, and over here 4 plus whatever and 2 plus whatever, they've got to equal the same number when you're balancing these. And that's the end of 9.2. I'll see you soon.